Hello guys, in this lesson I'm going to talk about the centripetal force and how to calculate it in an easy way that you'll never forget. Alright, so what is the centripetal force? Well, the centripetal force is actually any net force that causes a uniform circular motion, right? As simple as that. So if you use the Newton's second law, we know that the centripetal force is actually the mass times the centripetal acceleration. And if you remember, the centripetal acceleration is the velocity squared over r, the radius of the circular motion, or the r times the angular velocity squared. Well, you can just add this in this formula here. So we know that the centripetal force is actually the mass times v squared over r, or mr angular velocity squared. An interesting thing here is that we isolate the letter r. We notice that the radius and the centripetal force are inversely proportional. So if we have an object performing a circular motion at a certain constant velocity, okay, we have a certain radius, okay? However, if we decrease, for example, the centripetal force, the radius will increase, all right? And the inverse is also true, right? If you're having doubts or troubles about the centripetal acceleration, okay, you can check out our video we have in the channel about the circular motion. We use this formula, which is okay. A practical application related to the centripetal force is related to banked curves. I bet you have already seen something like this in those racing tracks where the curves, they're actually banked, all right? They're not flat. So why they do it? Well, let's consider a car here in a flat surface, all right? And do the balance of forces. So we have also this car here, it's turning left, okay? So it's performing a circular motion here, right? So we have the weight of the car, of course, pointing down to the center of the earth. We have the normal force pointing up here, perpendicular to the surface. And we have a force that's pointing left because the car is moving left. And this force, the centripetal force, and in this case here, is the same as the friction of the tires, right? So the car doesn't slip. Okay, so what happens now if we increase the angle of this of the road here? Well, now if we bank the curve, we have this at a certain angle. Let's do the force balance for this situation here. So we still have the weight pointing to the center of the earth, all right? And now we have the normal force, but the normal force, remember, is always perpendicular to the surface, okay? Again, if you're having troubles with the normal force, you can check out our video about normal forces, all right, where we explain it better. But let's continue here to our situation. So we have this normal force banked, tilted to the left now because of this angle. We still have the friction from the tires that's pointing in to the center of the curve so the car doesn't slip, okay? And now we have the centripetal force also pointing to the center of the curve, okay? So you notice that now that we banked the curve, we have a component of the normal force that's actually helping the centripetal force, the circular motion. So because of this angle here, we can actually reduce the friction on the tires. So that's the main cause why they bank those curves, because at high speeds, the friction would be very, very high on the tires, so the car would slip. If we bank the curves, now we can reduce this friction on the tires, all right? So now that we know about these banked curves, we can calculate the ideal banking. So what do we want? We have this situation here. For the ideal banking, it's a curve at a certain angle that we actually can reduce the friction on the tires to 0. So just the normal component here is enough to perform the circular motion. So what would be this ideal banking? So for the ideal banking, the net external force equals the horizontal centripetal force in the absence of friction, all right? So this component here, the normal component, should be the same as the centripetal force, all right? So if we do our balance here, our force balance, in the vertical direction, we have that the normal times the cosine, this component, it has to be equals the weight, all right, mg. And for the horizontal, we want this component here and sine of the angle to be equal to centripetal force, or mv squared over r. All right, now we can isolate from equation number 1 the normal force, all right, and add it into equation number 2. Can cut this mass here on both sides, and now we have sine over cosine. This is a tangent of the angle, okay? So we can isolate the angle to find the ideal angle for the curve, the ideal banking, okay? All right, now it's your turn to put in practice all those things we talked about, all right? So this is a picture of the Daytona International Speedway in Florida, all right? And the curves here are very, very steeply banked, okay? So it helps when the cars approach this curve in very high speed, okay? So just to illustrate, to put in practice what we talked about, I want you to calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. In other words, at what speed can the car enter this curve here and perform this circular motion without any frictions in the tire, all right? So do your calculations, comment in the comment sections your answers, and see you next time.
Physics can be easy. Subscribe to our channel and learn with the geeks.